different experiment than the last one you did. It's different. This isn't
I'm
necessarily.
Itaku. I know a lot of you, some of you I don't. Hopefully we'll get to meet and chat in the next weeks. Welcome to the first DLS of fall 2025. The first two sessions are going to be faculty slam, so short talks by not all, but most of the faculty to sort of give you guys a sense of what we all do, and at least the way I would be thinking about it is, who can you ask questions about what types of topics, right? That's maybe the thing to keep in mind. I'm going to be hosting for the next 2 semesters with Sarah Warks, who I believe has an announcement.
Oh, if you're registered for the DLS class, there's a sign-in sheet over there, and then we'll chat briefly at the end about expectations.
So after this session, we'll stay in the room for a bit. All right, so then without wasting any more time, Lauren is first, and then we'll just go through without introductions.
Great. All right, I'm keeping myself honest here. Hi, I'm Lauren Bergenheyer. I'm a sedimentary geologist, and I dabble in geochemistry. And I put this slide together to highlight, sort of in the red boxes, some of the different research topics I've tried to tackle along with excellent students and collaborators over the years. Today, I'm really going to focus in on the work we've been doing in critical minerals and coal the last 4 or so years, where I've had the pleasure of leading a very awesome team. And I'm going to put this pointer on for anyone else. And a really awesome team, many of which are here in the room. Critical minerals, we're going to talk here about our work in coal, and we're going to talk mostly about rare earth elements, which are a subset of critical minerals shown on the periodic table here. And note that this is divided into light rare earths and heavy rare earths. And there are some rare earths like praseodymium, neodymium, terbium, dysprosium that are sort of in more dire need or more critical rare earths relative to others that are considered a bit more excessive. So the word critical really comes from the idea that these are things that we're using in many modern day technology products, and specifically rare earths are important in magnets. And many of these are have supply chain bottlenecks or certain sort of restrictions, and we are looking for sort of some more domestic resources and innovative ideas. Many of you may think about critical minerals or rare earth ore deposits, and you might think of some of the higher grade ores that come from magmatic processes that concentrate rare earths. And these are called primary deposits, like those in Mountain Pass, California. These tend to be higher grade ores. And so you might ask yourself, why look for rare earth elements in coal? That seems like a strange choice. Well, actually, sometimes rare earth elements are formed and sort of concentrated through weathering and transport in sedimentary deposits and sedimentary rocks. And specifically, coal and associated mudstones actually offer heavy rare earth element enrichment that often these primary ores do not. And that, in combination with the fact that there are innovative mineral separation and processing techniques being developed right now, right here on this campus, that could actually allow us to process low-grade ores. So if you look at this plot that actually Peyton made here as part of his thesis, you see that the coals that we've been studying across Utah plot in this economic viability place of promising, potentially even, especially because they contain a lot of these critical rare earths like dysprosium, praseodymium, etc. So, are there actually critical minerals in coal and adjacent strata? Yes. We've been studying these coal-bearing strata across Utah and western Colorado. We've looked at 51 localities in total. We've collected something over 12,000 portable X-ray fluorescence points, over 400 ICP-MS data points to try to extract trends, geologic trends. And specifically what we're finding is that about 40% of the mudstone samples that sit above and below these coal seams are enriched in rare earths. When I say enriched, it's still pretty low. It's greater than 200 parts per million rare earths. So sort of an initial sorting. And then the coals in general are actually pretty depleted. So that sort of begs the question, maybe there's a model where you mine the roof and the floor of an underground existing coal mine, separate that material for rare earths. I do want to point out though that about 10% of the coals themselves are enriched. These are sort of the needles in the haystack. And so we've been digging into why is this small population of coals rare earth element enriched. And this was the focus of some of Hayton's work in his thesis. And this earlier paper was sort of a focus of Haley's first PhD paper. And so what we found is that actually the coals that are rare earth element enriched that we see across the region actually show a lower coal quality. In other words, they're kind of dull, they may have more ash content. It's actually not the stuff you're going to put in the power plant to actually burn for coal. They seem to be almost mutually exclusive. However, just an update on, well, why are the rare earth elements there? We just completed this study. This was Laura Wilcox's MS thesis that just came out in publication last week. And she was able to actually image some of the rare earth element enriched samples over the NanoFab lab using SEM and EDS and identify sort of three populations of monazites and a few xenotime minerals, grains that are enriched. Silt-sized grains, clay-sized grains, and then organically rare earths that are within organic matter. And so what that sort of allowed us to come up with is a somewhat viable mechanism so far in which there's a combination of paleodepositional controls and diagenetic controls on these rare earths. Specifically, probably a lot of the silt grains have been transported detritively into the coastal swamp environment where these peaks were formed. And perhaps the clay-sized grains come in through volcanic ash or airfall. And then potentially burial and late diagenesis may actually move the rare earths out of the coals and adsorb them into clays in the shales. And then finally, we see evidence that the organic matter itself actually in the plants were uptaking rare earths as well. So that's it for now. Thanks.
Next. Hello, everybody. My name is Brenda Bowen, and I am also a sedimentary geologist. But I am interested in sediments that typically are forming in situ, things like salts and iron oxides and clays that are forming from interactions between our surface and different rocks and organisms with the atmosphere and with fluids interacting with surface environments. Here's my aerial photo over from the drone overlooking the salt flats where I've done a lot of work, and I'm not going to say much about that today because I get to give the first full-length DLS in 2 weeks where I'll talk about work on the salt flats. So this is a little sneak preview. Stay tuned. Come back for more of all the details on that. I, through the years, have also had opportunities to hold many administrative roles, and so currently I have the unique opportunity to be the chair of the Atmospheric Sciences Department. So if I'm not hanging around here, it's because I'm over in our new building, new Applied Science building that's adjacent to the historic Stewart building. Come over and visit sometime. There's some really cool labs and instrumentation over there. But yeah, that just opened a couple weeks ago. Brand new, amazing space that we're sharing with physics and astronomy together with atmospheric sciences. So I've gotten to learn a lot in the last couple of years doing that about things like boundary layer processes and atmospheric dynamics and air quality, and a lot of amazing work going on over there. A lot of earth science happening, geoscience happening in that department too. So something you might keep your eyes out for what's happening in their seminar series and what courses they're teaching if you're looking to extend your geoscience opportunities. Another interesting role I play as an administrator right now is I'm the Utah lead on this giant project called the Futures Engine in the Southwest that's funded by the National Science Foundation. They awarded us a couple of years ago to start this engine, and it's up to $160 million over 10 years. And the aim is to incentivize, advance, and accelerate startup technologies that are going to help solve some of the challenges in the Southwest around water scarcity, energy needs, and things like air quality We used to talk more about carbon management, but lately we talk a little more about air quality. But trying to really advance science to become more commercialized. So where are the technologies that are currently in research development that could be commercialized with startups and then go big to actually solve some of these problems at scale. It is a vast project that sometimes I think, how did I find myself in this room having these conversations? But it's really fascinating. It's led by Arizona State University. We're currently competing for our next round of funds. So they said up to $160 million, but you only get a little bit at a time, and you have to keep competing for it. So I'll certainly share as there are more opportunities for people to get involved in that. I teach things like field methods. I've had the chance to teach field camp with Sarah this last year, and I think we'll be doing it again this year down at the Rio Mesa Field Station. I'll also be teaching oceans in the spring. And I love learning about perspectives different than my own. In my science, I like to use lots of different tools, so very much a field-based geoscientist, of getting out in the field, making measurements, making observations, but then also using all kinds of remote sensing data, satellite, multispectral, hyperspectral, INSAR, LIDAR, radar, whatever might help answer questions about how surface landscapes are changing. And I wanted to show this Modus image of North America just to highlight two of the places I've been working the most lately. Bonneville Salt Flats here that we'll hear a lot more about in 2 weeks, but then also the Colorado Plateau and Colorado River Basin, where working with Carrie and others to try to understand what's happening with all of the sediment that's going into Lake Powell that's now being exposed and remobilized and doing super interesting things in the landscape. And you can see on this scale, pretty unique landscapes that have some interesting stories to tell. And then finally, I'll just leave us with a little plug for in 2 weeks. Come learn all about the Bonneville Salt Flats, work of many PhD students and a lot of different partners, and look forward to sharing more about that. So, introduce our next presenter, Dave Bowman.
I've got props.
Maybe if you're right on the edge, shoot it so people can see us.
All right, this isn't a new one, but it's an old one. Before you join us in the spatial group, you'd better be okay with poop. Organic. Man, I'm in the wrong key. I knew this was dangerous. I gotta start without the music. Let me get the key. All right. So you got that. Organic. Skins are filled with isotopes that tell us stories if we know fractionation and invoke an isotope. An isotope. How substrate mixing leads to this source for biosynthesis. It's anything deltas of million ways to get those values to write it up. We'll need a model.
I graciously yield my time to encore.
Damn it, Gabe, it's 2 years in a row you've done this. Okay. I can't follow.
Sing it.
Trust me. No. Yeah, we discussed interpretive dance, but that's not going to go either. All right, so I can't follow that. All right. All right, so kind of the unifying theme of my research is how landscapes develop. Some people call it critical zone science, some people call it earth system science at a small scale, but for over 20 years we've focused on how energy and water in an open system thermodynamic framework influences the development of bare rock into soil and organisms and the interactions with the atmosphere. So on the long time scales, how do these systems develop? And on the short time scales, how does the structure that develops as energy flows through these systems influence things like carbon storage or water cycling? Over the last several years, we've been moving more and more towards just focusing on water, and that's because we've got big issues with water. Probably heard about it, the Great Salt Lake, the Colorado River Basin. We're trying to address these. So move from some of the basic understanding that we've gained over, not just my group, but many groups have gained over 20 or 30 years, and move it into the way so we can try to adjust some of these questions. During my sabbatical in 2021, 2022, I had a chance to work with Bea Gordon, who's a postdoc, also the daughter of the Wyoming governor. So the mix of science and politics comes here quite often. And we published this, we called it a data-driven review, and said you really need to know 3 things to better predict water resources, and we made huge advances, but they're not being incorporated. One is how much it's going to snow. Is that surprising? Right. I don't think many people would consider that very surprising, right? How much precipitation? The other 2 were what happens to the snowpack when it's there, and then where does snow go when it melts? So there are lots of common assumptions about this: temperature melts snow, not really, and that snow melts and runs off the surface, not really. Those are common misconceptions that still guide water resource management today. Those are the things that we needed to make progress in. We've been working on this idea, trying to make progress, and here's a bridge between basic research. You would think if you're interested in the amount of water resources, you'd be interested. This is a hydrograph for City Creek. So running from October 1st to September 30th, of how much stream flow came down City Creek for 120 years. Primary focus on most hydrologists, most folks, is how much water is in that peak each year. That's how much we have to use. In the critical zone, in the biogeochemistry world, we focus on the variability here. There's tremendous variability here. And it turns out that that variability there is quite large. And you might say it's idiosyncratic. Each catchment, that's something that's unique to that catchment. What kind of trees, what kind of rocks, how steep it is. Individual characteristics. That's a classic sort of approach in hydrology. At each site, each catchment is individual. What we found is all throughout the Great Basin and throughout much of Colorado, all catchments behave this way. It goes through about a 13-year cycle of peaks and valleys in terms of how much groundwater, so how high this is as a metric of how much groundwater is stored in the system. And all throughout the region, we have this same cycle. That's not by chance. That says that there must be some sort of external forcing. So working with one of Brenda's colleagues in atmospheric science, Luke Stone, who was advised by Court Strong, he was also a student in the hydrology program that I direct, identified a teleconnection between the North Atlantic and El Nino, ENSO cycle in the Pacific Ocean that controls precipitation here. And this figure here is probably the coolest research that I've ever been involved in, because we have no predictability about how much it's going to rain or snow in northern Utah or in the Colorado River Basin. ENSO has no predictability. North and south it does. And it turns out it's mediated by this teleconnection from the North Atlantic. We can now predict how much precipitation is going to come with a pretty high degree of accuracy, 6 or 8 months in advance. That's incredible. Once that snow falls, this is work by Bailey Olds, the snowpack is sitting there, and the snowpack is not static. It's responding primarily to solar radiation, solar energy. That's the big driver. This is one of Bailey's sites in Big Cottonwood Canyon. And you can see it, here's what it looks like in winter. And as it starts to melt, you can see variation in how the snow is ablating, how it's losing, associated with long wave radiation that comes off a tree, and then it stays much deeper in shaded areas where the tree shades it. And emphasize this point, it's not temperature that's melting the snow, it's the radiation. So that leads Bailey to ask, how can we manage forests? How can we create designer forests that minimize? This is the amount of snow that's lost over winter in high energy sites. This is the amount of snow that's lost in low energy sites. It's lost as vapor. It's not available to anyone. It's not available to plants. It's not available to streams. And so Bailey is creating designer forests to manage the water resources that come in by changing the local hydroclimate. And then the last question, the last of the three, how much it snows, we addressed with Court and Luke. What happens to the snow? Bailey's working on, and others. And so where does the snow melt go? And so this was a sabbatical project where I drove around the western US and visited lots of students and postdocs that I used to work with. And it turns out that the water coming out of the streams is much, much older than we would have anticipated. It takes about 5.5 years for a water molecule as a snowflake to make it out of the stream. It doesn't run out of the surface. And the fact that it's in the ground means that it can contribute to the stream, and plants can get their pesky little roots on it too. So it's this thermodynamic competition for water in the system. That's incredibly important because the amount of water that's stored controls runoff efficiency. Runoff efficiency is just the ratio of the amount of water that exits at stream flow that's usable to society divided by the amount of precipitation that fell. The higher number, more water comes out. That tracks with how old the water is, which varies based on geology. Geology term in one of my talks at Route 5. Pretty simple, incredibly simple. It's really high and low permeability. It tracks with how old the water is, and it tracks with that level, that very small variability in groundwater storage we talked about a few slides ago. So you put those things together, we can predict how much snow is going to fall, how efficient that stream flow generation is based on the groundwater storage, and how efficient that stream flow is based on the amount of water that's lost. So we have developed these very simple transferable models, and before the most recent election, we were porting them into NOAA, the River Forecast Centers, the USDA, moving this into stream flow prediction. Unfortunately, that's all on hold, so let's keep our fingers crossed that we can start to get better management, improved management into a vibrant workforce that still exists.
All right, so I'm Juan Carlos. I arrived here at the U in early 2023. As you can imagine from the courses that I teach, I'm a petrologist and a geochemist, mostly a metamorphic petrologist dealing with water-rock interactions. Some fun facts about me: I grew up in Guadalajara, Mexico, which was recently named one of the best places to visit in the world, contrary to what the news might say about Mexico. I got into earth sciences because like I climbed a lot when I was younger. And at some point I wanted to climb Denali. And in case you don't know, don't jump off a moving train. I did it once and it's not something that I'll recommend. So what do I do? Again, I mostly deal with fluid rock interactions. That's a logo that Dino Red graduate from the department made for the lab. And I use both natural samples and experiments to try to understand how chemistry of the rock change and how like these fluid rock interactions will result in changes. This is a sample from Mexico, like a serpentinite that has been weathered, and we're using that to try to understand subduction zone processes where like there's transfer of fluid from the slab into the mantle wedge and how like the elements are cycling. I also use experiments to volunteer some pictures. This is Harrison and Tori in Antelope Island sampling some ultramafic bodies in the Farmington Canyon complex. This is Mexico sampling these peridotites. And this is a sequence of carbonated peridotites from Oman where we're trying to understand both like subduction zone processes and try to understand how can we reproduce these kind of systems through engineering to take carbon out of the atmosphere. I use also experiments using both like pristine minerals and rocks to try to understand kinetics and how fast reactions happen. Right? Usually at the temperatures that I work with, kinetics become very important rather than thermodynamics. And thermodynamics will tell us one thing, and then we see that kinetics are pointing in a whole different direction. So we're using a lot of kinetic experiments to try to understand some of these fluid rock interactions. Some of the projects that students have done here at the U, one is Harrison Patton that is working on these rocks from Mexico, trying to understand the petrology and geochemistry of the Vizcaíno ophiolite using major and trace elements. And one of the things that we have found that has not been described before is that this small ophiolite in Mexico is like C-rising close to what you'll expect from a 4-arc or a mantle wedge serpentinite. So we can actually look at subduction zone processes looking at these rocks. Dino Red did an experimental work on understanding how brucite in these rocks, like this rock has a lot of brucite, how it dissolves over time to try to understand how much magnesium will be sourced from these rocks into ocean chemistry. There has been a huge change in magnesium to calcium ratio over the past 80 million years, and that kind of coincides with the opening of the Atlantic at exposure of mantle peridotites in the seafloor. So we're trying to see how much magnesium can be sourced to water-rock interactions into this. Then Lauren is working on kinetics of olivine alteration. Olivine alteration is usually thought to be very, very slow at low temperatures and essentially non-existent below 150 degrees C. But there's evidence that like these reactions are happening. So Lauren is using anisotopic tracers to try to see precipitation and dissolution of olivine during these processes using an isotopic tracer. And recently, Alani joined my group to work with her PhD. Is still on a project to be determined that I'm hoping that will be one of these three, again, element cycling during seafloor weathering. I'm particularly interested in what happened during weathering of the seafloor. This is a plot on uranium and thorium. This is what you'll expect from a magmatic trend. And a lot of the mid-ocean rich serpentinites are enriched by a factor of 1,000 of uranium. But that requires that there's like 300 kilograms of fluid going to these rocks and increasing the amount of uranium. This has implications for lead isotopes over geologic timescales because this enrichment generates small fractionations in uranium. So over time, that will change the lead isotope ratios. Again, this is model magnesium to calcium ratio, which increases over the past 40 million years, starts to increase about 60, which is the opening of the Atlantic. So I'm interested in how much contribution from seafloor weathering and release of magnesium from these rocks contribute to this change. I'm starting a project on trying to understand the origins of ultramafic pods in the lower crustal rocks from the Farmington Canyon complex. There's still a lot of debate on where these come from. And I'm working also on applications of geological processes. One is trying to understand how nickel and cobalt mobilize during ultramafic rock alteration. Nickel and cobalt are critical minerals, as Lauren was saying, and we know that they're mobilized during fluid rock interaction, particularly in ultramafic rocks. And depending on how much water the rock is seeing, it'll be hosted in different minerals. So we're trying to understand how that happened to try to find new sources of nickel and cobalt. And finally, I'm working on carbon mineralization, ideally with hydrogen generation as a secondary product. Carbon mineralization has been explored as a potential way to take CO2 out of the atmosphere. One of the big problems is that it's waste management, right? Like there's no economic incentive to try to do carbon mineralization. So it's an expensive process, and if you don't have something to sell for it, like nobody wants to do it. So we're trying to understand if it's possible to generate hydrogen out of these reactions and then do the carbon sequestration, and then you can sell the hydrogen as a source of energy. That's it.
Alright guys, I already introduced myself. I'm a research associate professor. I've only been here a little over a year, so still getting established. And my office is 321 if you're interested in chatting. And Gabe introduced some of the things I'm going to talk about, but I'm going to go through sort of the oxygen isotope system as an example of how we as isotope geochemists think about things, and the power of measuring isotope ratios in different materials. So we know oxygen is very important for many reasons, and more specifically when it comes to the work we're doing, we're interested in what phases or what forms does it exist in nature, and then how are processes transitioning, in this case oxygen, from one form to another, and can we track that using isotope ratios? So on the right is a very common plot. It's what we call the triple oxygen isotope plot. It has the delta 17O on the Y and delta 18O on the X, and that's essentially just a measure of how different the isotope ratio of a material is from an arbitrary standard that we as isotope geochemists decided has a value of 0. And then it's all built on that. It's great. So general rules to think about: light isotopes prefer being mobilized or utilized by biology. Evaporation favors light isotopes. And heavy isotopes prefer to be in solids. They stay back. And this is due to the particularities of differences in vibrational energy of bonds. We can get into that later if you want. But we can use the changes or the fractionations, as Gabe mentioned, to uncover processes when we measure things in the field or in the lab. And there's two different types or categories of fractionation specifically related to oxygen. Mass-independent fractionation exists in other isotope systems: sulfur, mercury. There's a few, but oxygen's sort of like the famous one. And the key takeaway here is that you have sort of diagnostic zones for different types of material. And that's because we have sort of mass-dependent processes occurring sort of at the surface, under what we would consider sort of normal geochemical conditions, and then you have processes that violate the mass-dependent rule that are occurring usually in high-energy environments. In this case, stratospheric photolysis producing ozone creates a mass-independent signature that is then transferred through atmospheric chemistry down into various species, and then we have the chance to measure that occasionally. One of the things that we're going to do with this is use it, because we have distinct triple oxygen isotope compositions for water and air. The details of that don't need to be known at the moment, but if you know you have distinct compositions and you know those two reactants are participating in the production of something, you can now use those distinct isotope ratios as sort of tracers. And in the case of uraninite, we're going to do, me and Tessa, I don't know if she's in here, we're going to produce a line that can produce oxygen gas from solids and be measured on a mass spectrometer. And when you do that, for uraninite, for example, you can use the isotope composition of the O2 gas that you make to start to model what reactions produce this phase. And so we'll see this type of use of oxygen isotopes in a couple different scenarios. So this is about to come out in EPSL actually. This is a picture of Rio Tinto. It's an acid mine drainage site. There's green water, totally different chemistry mixing into the main red water. Colors are both due to iron in different oxidation states. So green is Fe2+, red is Fe3+. And that also is tied to sulfate concentration. So the green waters have the highest sulfate concentration. It's being diluted into the red waters. And then you see that reflected in 3 isotope space as well. So the green triangles are the green water data, and the red are from the red water. And that's telling us through some modeling, as Gabe said, that the green waters are being dominated by a fractionated air oxygen as the dominant oxygen source, and then that's mixing with an end member that's dominated by water. And so that's a use case. And then there's some more exotic stuff that I like to do as well, looking at soluble organic matter and soluble inorganic species leached from meteorites. And what can we say about the origin of solids in the solar system? We have a really unique data point that's in an AGU abstract that has kind of, it exists in a place where no one's ever really measured anything up to now. And so the trick is, right, this is where sort of normal terrestrial materials exist, extraterrestrial materials can exist above this line, but are usually bound to below this other line. And so we've broken that rule, and now we have to come up with an explanation for it. And so that's what I do, and it's quite a powerful tool.
I'm going to start my clock too. My name is Jim Carner. I'm a research faculty here. I look at mainly extraterrestrial rocks. My main job is that I'm the leader of the field team that goes to Antarctica for the U.S. program and recovers meteorites. This is just a great picture of an ice field to the right and a moraine to the left, and all those red flags were meteorites we recovered from that moraine. So that was a super productive area to find extraterrestrial rocks. Antarctica is covered with ice. It has been covered for several tens of millions of years. And basically the concept of why meteorites are concentrated there is that if you think of Antarctica as an overturned bowl of ice, the ice can be about 2 miles thick at the South Pole, kind of in the center of that continent there. And then, so the ice is basically, the ice sheet is sliding off the continent to the peripheries as glaciers. As those glaciers move towards the coast, they can be obstructed, and up from that red dot, kind of veering off to the left there, is the transantarctic mountains. And they poke through the Antarctic ice. They stall these glaciers, they slow them down. Eventually the surface is whittled away, and meteorites that had rained down on the surface and were covered and were incorporated into those flowing glaciers basically are exposed in blue ice areas in those transantarctic mountains. So we look for those transantarctic mountains, and we look for blue ice areas. There's a little cartoon of the meteorite concentration mechanism. Meteorites are falling down, being incorporated into the glacier. flowing with the glacier and then being ablated away when they're obstructed from their flow. Blue ice is just deep blue, old ice, densely packed. Those areas have come to the surface, basically are exposed at the surface. That's where we find the meteorites. The right picture there is what they look like in satellite imagery. This is the ice direction is to the right there, and you can see blue ice is exposed. This is right outside of that Allen Hills area in Antarctica. And there's what a meteorite on blue ice looks like. So we look for those blue ice areas, and then we go and try to recover meteorites. The meteorites concentrate on the ice itself. There's one of our mountaineers approaching a meteorite there on the blue ice. So those are easy to spot there if there's not much terrestrial rock. But we also find a lot of meteorites in moraines. So those are on the periphery of glaciers or the middle of glaciers, or anytime you have this kind of collection of terrestrial rock that the glacier has been kind of pulling along and pushing along. And there's Julia Gross with a big meteorite she found in a moraine there. So the real goal of our program, and it's ANSMET, the Antarctic Search for Meteorites, has been around for about 50 years. We're the world's foremost supplier of extraterrestrial materials for scientific study. Over 1,000 papers have been written studying the meteorites that we've recovered from Antarctica. Every year there's about 70 or so peer-reviewed publications using our meteorites. Our meteorites come from basically 3 bodies in the solar system. The one on the left here, that's asteroid Bennu, so there's the link between meteorites. Most meteorites come from asteroids. Bennu was the subject of the recent US space mission where they actually collected a sample of Bennu. So our meteorites not only make the connections between asteroids, but we kind of bridge the gap between planetary science that's being done by rovers and explorers and flyby missions to kind of ground truth. And then we also have an iron meteorite. That's like from the core of a differentiated asteroid. So the first one there is kind of an undifferentiated chondrite meteorite. And then we have meteorites from the moon. That's one of my favorite meteorites we ever found. It's kind of a mini-me of the full moon there, where the black matrix is volcanic basalt, and the white grains there match the white parts of the moon. That's a calcium-rich feldspar. And we also, our program is the first identified Martian meteorite. So they will provide ground truth to the space missions and rovers and helicopters and landers on Mars. Thanks.
Maybe we can advance to the next person's slide at the end of our talks. Thank you.
My name is Marie Jackson. I'm a research professor in the department, and I would like to point out that all concrete fractures, even concrete in the Sutton building. And some of you may have actually noticed some of these long fractures with linking microstructures, which are similar to fault segments in rocks. There's some excellent examples just over here next to the graduate student offices in 291, but the students don't need to worry. That's because the structure of the building is a reinforced framework of steel. However, fracture in marine Portland cement concretes causes great damage. That is because seawater moves through the fractures and chloride attacks the steel reinforcement. I'm sure you've seen examples of these kinds of failed concrete, Portland cement concrete structures. The United States Army Corps of Engineers Engineering with Nature program has a very different concept for building in shoreline and marine environments. And ancient Roman builders also had a very different concept. They deliberately employed self-sustaining processes in these massive concrete structures, which are still functioning today. And those principles of beneficial corrosion and self-repair underlie our research and our EWN project. We have been making a Roman analog marine concrete for more than 10 years. We use Roman methods combining hydrated lime, volcanic tephra, and seawater to make a mortar that binds coarse clasts of pyroclastic rock or carbonate rock. That's called caimenta. Those large clasts actually form a conglomeratic framework that reinforces the concrete. We have also been developing an arc bending test to measure mechanical resilience of concretes. In that test, we apply a load to the top of the arc and we measure a crack mouth opening displacement that's produced by the stable nucleation and propagation of a microcrack. In the Portland cement concrete, after 3 tests over 3 years, each test is followed by renewed hydration, the concrete doesn't recover and in fact loses a tremendous amount of carrying capacity. In the Roman analog, the concrete actually recovers its previous load-bearing capability and then exceeds it. Why? Well, that damage zone in the Roman analog concrete is composed of innumerable tiny and echelon microcracks, which simply cannot carry very much opening displacement. And when we make in situ gas permeability measurements of that damage zone, we find that the concrete hasn't even changed permeability in that damaged area. The Portland cement concrete, by contrast, forms a large fracture, a very large permeability difference, and simply doesn't have the ability to repair that long discontinuity. We have a vision for this material as a sustainable, tunable, and biocompatible cementitious material for applications with extreme durability and longevity. These are some of our ongoing experiments at the ERDIC lab in Vicksburg, Mississippi. This is a national lab funded by the Department of Defense. Some really promising news: the American Concrete Institute has a new committee on seawater concrete. We've just integrated Roman principles into the mission statement. So, do you want to learn more? If you do, please stop by 273 FASB, and we can also map some cracks in the Sutton building concrete.
Hi, I'm Sarah. I arrived at the U in 2018. Yes, I define myself as a petrologist, high temperature geochemist. I'm interested in many things that is related to magmas and volcanoes, and in my group, the 2 main questions we are trying to address are how magmas are formed in the mountain and what happens to them when they travel to the surface. And for that, we are using a combination of high pressure, high temperature experiments, in situ analytical equipment, instruments like the electron microprobe or the laser ICP-MS, thermodynamics and geochemical modeling, and thanks to the arrival of the new thermoneoma isotope geochemistry on bulk rocks very soon. I'm not sure I followed the assignments, but I was not there most of last year because I was in sabbatical, so I decided to talk a little bit of what I did when I was not there. So I actually spent a good portion of my time last year in Europe, And I'm not a field geologist, but I still enjoy seeing some nice geology. So I started my sabbatical with two field excursions. The first one in Iceland, that was very cool because we went with the whole group, and that was to wrap up the work we have been doing on an expedition I said on offshore Norway a few years ago. And so that was great. And then another short expedition in a very nice area called Cabo Ortegal, which is a national park that shows some of the 101 pristine example of outcrop of a heterogeneous mountain lithosphere where you see very nice level of peridotite and pyroxenite, even if the weather was not so great, but the geology was very good. And then I split my time between these various institutions. The goal of a sabbatical is to develop new collaborations, trying to take new ideas and new projects. But importantly, I also spent some time trying to acquire new skills, I would say, and part of them were doing high pressure, high temperature experiments. The project was to look at formation of carbonatitic magmas, but in particular I learned how to do this double capsule techniques that allows you to do experiments that contain volatiles. And I also spent some time in Cardiff learning how to do some column chemistry. As I said, we are going to have a new thermoneuma, and I want to use it, so I need to know how to do that. And hopefully, and also thankfully, I did some tourism and saw my family, so now I'm ready for a good year to start and what's come next. And that's going to be an exciting year because it's actually a lot of things is happening in my group. So Ashley is going to have her quartz later on this semester. So Ashley is working on how the lower oceanic crust is formed, and she's using a combination of high temperature experiments and analytical measurements on natural samples. Emily is entering last year of PhD, and she's studying magmatic processes during the development of a passive margin. So basically, what are the controls that will result in having a lot of magma or no magma at all when a passive margin is being created. And so we also have like two new projects that we want to work on. The first one is Kuhan, who is going to look at who is going to lead the project regarding what is the role of the mantle lithosphere in intraplate magmatism. And later this semester, AG is going to join our group to look at what is the effect of volatiles on the melting behavior of pyroxenites. And these two projects are directly using what I actually learned during my sabbatical last year, so I'm quite excited to start these two new projects. And just a note about teaching to finish. Those are the classes I'm teaching in the department. I have taught in the department so far. This semester I'm teaching mineralogy, and I just wanted to point out that next semester I will be offering an advanced Igneous petrology class, so if you are interested about learning about this, do not hesitate to contact me and ask me a question about this. And thank you.
Definitely didn't follow the assignment. So I'm Will Levitt. I'm new faculty here as of January. I was at Dartmouth College for about 8 years, and then you guys convinced me to come here. I really appreciate it. Give me the opportunity to come here. So my work is sort of split, or I should say my group's work is split between thinking about two things. How do we find life elsewhere in the universe? So NASA has been a great supporter of our work. And then how do we find life here on Earth deep in the past? So these are kind of the two challenges, the grand challenges. So I would say I'm a geomicrobiologist or a biogeochemist, mix and match, I would choose. I am fundamentally obsessed with microorganisms, but I'm also interested in how they impact planetary processes. And I think of this as the space-time problem. We do experiments in the lab over the course of a few days, weeks, hours, maybe months, if you really want to torture your grad student. But we're interested in, again, planetary scale processes. So how do we make this coupling? This is not super straightforward. Molecules and isotopes. This is really what Kate was telling us about, I think. So we're going to think about how can we use stable isotopes, in particular, in biomolecules. Yes, there's lots of other cool materials on Earth. that you can all teach me about, but I'm in particular interested in things like lipids that exist in the membrane of microbes, in particular the ones that live up in Yellowstone and up in the Great Salt Lake are the two areas I've been working lately. And we're interested in the composition of the isotopes in them. So most biomolecules are kind of stuck with hydrogen and carbon. Through some of the new technology that folks like Isaku work with, we can start to look at the different placements within those molecules those isotopes actually sit. But we can use this because this is going to tell us something about the environment in which that organism was living, and also the composition of either the precursor, the carbon that it ate, or the hydrogen that it ate. And in the case of the hydrogen, it's almost always coming from water. So we can start to think about, ooh, maybe that's a paleoproxy mission. Just to give a sort of a big picture overview of the timescales over which you might be able to answer questions. I'm not going to talk about anything specific today. On log order time, with things like RNA, we can answer very short-term questions. So generally, as geoscientists, we kind of ignore this. It doesn't live for very long, the RNA molecules. But it can be useful for understanding how our organisms are operating. DNA, there's all hot debates in various, certainly paleontology and anthropology communities of how long DNA can persist in the fossil record. But sure, it can be really useful. And RNA and DNA are really fabulous encoders of information. Proteins, again, we can record a lot of that same information. They may be able to persist in the geological record even longer. But lipids are really where it's at if you want to start to answer what I would consider true deep time questions. And you lose a ton of information further back in time you go. But if you look at very diagnostic structures, like say a hopanoid or a steroid, so these two fun cyclic molecules up here, or even maybe a phytane, a plant-derived molecule, you can look. You as the sedimentologist is going to tell me a lot about the environment in which this thing was deposited. But then I as the biogeochemist can say, okay, well that's from this plant or this microbe. Let's look at its isotopic composition. We can start to unpack what environment that organism was living and how it was living. So this is sort of the bigger concept, is we can use these biomolecules and their isotopic compositions as windows into the Earth's past. There is a problem though. So sure, you as the geologist can tell me everything about this sedimentary rock, and probably more than I'm ever going to remember. But if we want to actually understand what these structures mean and what their isotopic compositions mean, we need to understand how the organisms that make them do that, and how that actually is going on today in our best sort of analog examples, to then interpret that biological record. So that's all I have for you about my science, or my group science. If you want to talk about hot springs, that's one of my long-term obsessions. That's how I got into science as an undergraduate. If you want to talk about salt flats, I'm learning about them. I have some awesome colleagues here that are going to teach me about that. And if you want to come play in the laboratory, come talk to me. We like to grow really weird things that take a long time. And then in terms of teaching, because that seems to be a theme, I'm doing evolving right now, which is awesome and Kathleen. I'm also co-teaching geochemistry with Juan Carlos. And then in the spring, I'm going to do isotopes with Isaku. And I also have a grad seminar, or I should say a grad class on writing and giving talks, which I think is probably the two most useful job getting skills. So we're going to do that all spring. So come see me. Awesome.
All right, I'm Lomiax. This is my group here. Unfortunately, we're down to just me and Audrey because we lost. But we do rock and mineral physics. So we specialize in extreme conditions and understanding how extreme conditions impact mechanical properties of various rocks and minerals. One of our major things is trying to understand what happens deep in the Earth's interior. So looking at things like the lower mantle and the core. So we're doing things where the pressure is more than 1 million times atmospheric pressure, or atmospheric pressure, and sort of thousands of Kelvin. And some of the things we try to understand are Earth's interior, but also things like impacts. And then in some weird tangent, we got interested in what happens to things when they're damaged by radiation. One of the things we do is a lot of experimental work. We use a variety of high pressure and high temperature deformation devices. So primary one is the diamond Hamel cell. So these for scale are about 3rd carat diamonds, and polished until it's flat. And we can trap a sample between them to generate high pressure. Because they're transparent, if you want, you can shine a laser through them to either up, or you can wrap them in a resistive heater and heat them up. This is in a vacuum vessel. It turns out if you make diamonds really hot in the atmosphere, they burn and make CO2, which is not good use in diamonds. Or you can do something like a multi-angle press. So this is a big hydraulic press. It's about the height of this room. And you can use those to basically squish rocks. Okay. What we do is we have these devices and we go to a particle accelerator called the synchrotron, and this produces intense X-ray radiation. This one is in Argonne National Lab in Chicago. It's about 1 kilometer in diameter. And to give you an idea of sort of how powerful those X-rays are, the kind of data we can collect in something like 1/10 or 100 of a second would take about a day on a conventional X-ray source to collect that many photons. So we can do these experiments. It sounds super exciting, but a lot of it is putting samples on the beamline or sitting in this experiment hutch where you're shielded from radiation with a bunch of computers. This is us with a group from Los Alamos and Livermore National Labs, so we work a lot with the national labs. And then what we do is we collect data on mechanical properties, things like deformation, behavior, strength, and we try to understand what happens to slabs as they go subduct into the earth. We also complement our experiments with numerical simulations. So this is a finite element simulation of two minerals. This light colored stuff is bridgemanite, which is the main component of the lower mantle, and these inclusions are ferroparticles, which is the second most abundant, and we're trying to study basically how to stress and strain partition within the sample. The other thing that we work on, kind of a new thing we've gotten interested in, is studying meteor impacts. And what happens is most of the devices I showed you on the previous page are something we call quasi-static, and basically we're squeezing things slowly. And the other main technique that people use to study things at high PT conditions is shock compression. So maybe the really famous one right now is the National Ignition Facility of Lawrence Livermore, where they're doing fusion reactions, so making helium from deuterium. Right? The idea is that you could have unlimited clean energy. And it turns out there's this huge gap in sort of the rate of these experiments. And for many years we had no data in this gap. And it turns out that meteor impacts have strength rates that form this gap. So one of the things we did is we built this device that uses the diamond amble cell like I showed you. But what we did is we put a piezoelectric crystal on it. So maybe you've clicked a quartz lighter that clicks and it makes a little spark. So you can put pressure in a quartz crystal and it makes an electrical impulse. Turns out you can do the reverse, which is you can put electricity through a piezoelectric and it'll expand and it'll do it quite quickly. And so what we can do is we can put a voltage pulse in here, basically we smack our diamond ample cell, and we can create strain rates at sort of meteor conditions. So if you want to make a simulation of a meteor impact, you want to know what the mechanical properties of those are at the correct strain rates. Why does it matter that we do it at the correct strain rates? Well, some minerals, this is zircon, which is a very common accessory mineral. It has a high pressure transformation from a phase called readite. People use that to infer peak shock conditions. Turns out, if you do an experiment quasi-statically, you get a pressure of around 20 GPa for that phase transition. If you do it in shock, it's maybe 40. So that's a pretty big error. And it turns out that the strain rate has a big impact not only on the strength of materials, but on phase transformations. Olivine, Sarah's super interested in olivine. So in the upper mantle, it turns out if you shock olivine, you get a different phase diagram. You don't get any of the same phase transformations that you get in the static experiment. And there's some really interesting physics that we don't understand. The final one I'll talk about, we started looking at radiation damage because of zircon. Turns out natural zircons have uranium. Uranium decays and it creates fission tracks. This is the other piece of this puzzle. And it turns out that radiation damaged zircon stabilizes the low pressure phase to higher pressures. So we started working with a collaborator at University of Tennessee who does radiation damage, and he takes zircon samples for us, puts them in a nuclear reactor, they get radiation damage, and then we can compress them to try to understand what the interplay of something like fission tracks due to things like phase diagrams at high pressure. You can also do some things. I was working on tungsten carbide, which is not a particularly interesting geologic material, but it turns out if you radiation damage it, you can make it like 2.5 times stronger, which is actually a pretty cool material science application. So we do a little bit of that, I'll quit.
That's it for today. Thank you guys. I'm amazed that we only went 5 minutes over. We'll try and do better next time. And if you're in the course, stay behind.